right, today we're going to discuss bearings and direction. Bearings and direction are usually used in word problems or application problems. Instead of it saying a direction angle, it would talk about a quadrant bearing or a true bearing. So let's kind of go over what a quadrant bearing or a true bearing is. Okay, so the direction of a vector can also be given as a bearing. Bearings are frequently given in application problems. That's what I just told you. Quadrant bearings is the acute angle between a vector and the north-south line. The north-south line is the y-axis. Now, looking over here, we have a vector given. Okay, see our vector, it starts at the origin and extends here in the fourth quadrant. Now, in order to identify the quadrant bearing, it has to be the acute angle between the vector and the north-south line, which is the y-axis. So the acute angle between the vector and the north-south line is this angle right here. So the quadrant bearing is going to be 60 degrees. Now, since it's in between east and south, we'll give it in directions of south 60 degrees east. Okay, south 60 degrees east, because it's actually 60 degrees east of south. So you put the south first and the east second, and that's how you would write a quadrant bearing. So if you see it written in this format right here, you know you're dealing with a quadrant bearing. Now, a true bearing is an angle measure that's clockwise. Now, in the past, dealing with clockwise, we know that those are negative angles, but with vectors, that's not the same situation. So it's the angle measured clockwise from the north of the vector. So you start north, so you start here and then you go clockwise, which would be around, okay? So the true bearing of the vector on the right is actually 120 degrees. So if you start here and you go to the vector, so that we know that this is 90 degrees, okay? And if this is 60, this would be another 30 degrees. So 90 degrees plus 30 degrees gives us 120 degrees for this angle. Okay, so a true bearing would be 120 degrees from the north line, which would be right here. And we go clockwise with a true bearing. Now, when you write a true bearing, you don't write south and east, okay? You only write the degrees. And they have to be written using 3 numbers. So if you have something like 15 degrees, you would simply put a 0 in the front. All right, now you have a little side note over here. When a degree measure is given with no additional directions, assume it to be a true bearing. If it looks like this, then you know it's a quadrant bearing, okay? So looking at number 1, we have our vector A, and it gives us 85 degrees right here. And we're wanting to find the quadrant bearing, and we're wanting to find the true bearing. Okay, so with the quadrant bearing, we know that it has to be the acute angle between the vector and the north-south line. If you want to write your directions down to help you out, that's perfectly okay. All right, so the acute angle between the vector and the north-south line, or the y-axis, is going to be this value right here. Okay, so we already have 85 degrees on this side of it in quadrant 1. So we know that this whole angle right here is 90 degrees. So 90 minus 85 is going to give us 5 degrees. That 5 degrees is going to be our quadrant bearing. Now we need to figure out, it's east of north, so we'll put north 5 degrees east. Okay, now our true bearing is going to be the angle measured clockwise from the north to the vector. So here's north to the vector, and that's also 5 degrees. Now, because this is a true bearing, it has to have 3 number values, so put 0, 0, 5 degrees. Number 2. Okay, so we have counterclockwise 212 degrees. Okay, we are wanting to find the quadrant and the true bearing. So remember, the quadrant is the acute angle between the north-south line and the vector. So that's going to be this value right here. Okay, so you see this part right here is 212. So what I'm going to do is I'm going to take my 212 and I'm going to subtract this 180 degrees right here to figure out what's left for this little angle right here, which is 32 degrees. Okay, so I know that this is 32 degrees. To find out this part, which is the acute angle between the north-south line and the vector, I know that this is 90. So I'll do 90 minus 32. Okay, and this part right here will give me 58 degrees. Okay, and that's going to be my quadrant bearing. Okay, I see that it's 58 degrees west of south, so I'll do south, 58 degrees west. All right, now let's find our true bearing. Our true bearing is from the north line clockwise to the vector. Okay, so this is 90 degrees and this is 90 degrees. That's a total of 180 degrees. Then I need to add the 58 degrees right here, and that's going to give me a total of 238 degrees for my true bearing. All right, I'm going to let you deal with number 3, so work that out and send that to me. All right, now let's look at our word problems. So I'm going to do number 1 and number 6 for you. You can do the other, or number 5. So you'll only have to do on this particular section number 3 and number 5. All right, kiddos, so an airplane is flying at a bearing of 245 degrees at 550 miles per hour. So let's think about what we've got here. We're talking about a bearing, so that's going to be a true bearing. If it was a quadrant bearing, it would be written like this, okay, of 245 degrees, sorry. So we've got going clockwise from the north. I always forget to do this. Okay, so that's going to be 9, 18, so that's 180, and we want to go to 245, which is going to be about right here. Okay, so going this direction, that's 245 degrees. Okay, now, if we're going to find our direction angle, we're actually going to go in the opposite direction and figure out from the positive x and go this way. So we know that this is 245 degrees. This is the angle that we're going to use. So let's now go in the proper direction. So I know that this is 90 and this is 180. I need to figure out what this value is right here. Okay, so since this one's 245, that's 180. I'm going to do 245 minus 180, which will give me 65 degrees. Okay, that's going to be my acute angle right here. Okay, so that's going to leave 25 degrees for this angle. So take the 180 and add the 25 degrees, and we're going to get 205 degrees from the positive x-axis to our vector. Okay, now we're wanting to take this and we're wanting to give the velocity of the airplane as a vector in component form. Okay, so here's my vector v, and I'm going to put it in component form. Now remember, our magnitude is going to be multiplied to the cosine, and our magnitude is going to be multiplied to the sine. What is our magnitude? Well, it's our speed, 550. So 550 times the cosine of 205 degrees, and then 550 times the sine of 205 degrees. Okay, so go to your trusty calculator, and let's compute these two values and see what our values are. So we have 550 times the cosine of 205, and then we have 550 times the sine of 205. Okay, so nice thing about this is that we do not have to worry about adding or subtracting any other types of values. Those are your two answers, okay? Let's go ahead and take these, since it doesn't tell us any directions, and go 2 decimal places. So my vector is going to be negative 498 and 47 hundredths, and then negative 232 and 44 hundredths. All right? Okay, so I said I was going to work out number 6 for you, but I've actually changed my mind. I'm going to let you do 5 and 6. On number 5, you have a 40-degree angle, so you don't have to worry about anything. 40 degrees, you're set, okay? All right, and so you just go ahead and you want to write this one in component form, so you'll do the exact same thing that I did right here, okay? Now, number 6, you've got a cruise ship sailing at 20 knots. The 20 knots is your magnitude at a direction of north 12 degrees west, okay? So this is going to be in quadrant bearing form. And then give the velocity of the cruise ship as a linear combination in unit vectors. So after you find this value, you'll put your I and your J behind them, okay? All right, so give these a try. I know you'll do great. So do number 3, 5, and 6. Y'all have a good day.